Hey, dropping in life's math and history, and we are going to take a look at the HL theorem. But before we understand this theorem, we're going to do a little warm-up because the word HL kind of has to do something. So how do you find the hypotenuse right here? In your earlier years of mathematics, if you ever did a squared plus b squared equals c squared, that's the Pythagorean theorem. Or an alternative would be leg squared plus another leg squared equals the hypotenuse squared. That is another formula you might have learned. So according to the Pythagorean theorem, there's our answer, but it has to be squared somehow. Here's an example. If we gather 8 squared plus 6 squared, it has to equal c squared, or the hypotenuse squared. Turn this into 64. 8 times 8 is 64, and transform this into 36. 64 plus 36 will equal 100. The square root of 100 is 10. So basically, C is going to equal 10. This question mark will now be erased because we know it's now the number 10. So that is the Pythagorean theorem. But now can you guess why we learned the Pythagorean theorem? Well, the reason why is, if we take a look at HL theorem, it has to include two things that we have already. Right triangles have right angles, which we explained 2 videos ago. It has a hypotenuse and 2 legs, and that's what exactly is going to happen. Here is the hypotenuse leg theorem. If the legs and the hypotenuse of one triangle are congruent to the leg and the hypotenuse of the other triangle, that is right, both have to be congruent. So let's use diagrams to understand this a little bit better, because sometimes pictures speak louder than words. So technically, if the leg and the hypotenuse of one right triangle, this is a right triangle, is congruent to the leg and the hypotenuse of another triangle, then both of the triangles have to be congruent to each other. This is a faster way rather than saying SAS, SSS, and ASA. This is another way we can prove right triangles. So now if we know the theorem, why can't we do the proof and end the video? So let's do the proof now. Proof given, but there's a little warning about this proof. About the hypotenuse leg theorem, unlike SSS, SAS, and SASA, there's a little problem with this theorem. There are rules that we'll have to follow that will catch up to us later if we continue. So the rules that will probably annoy us in geometry is, before you write hypotenuse leg postulate or hypotenuse leg theorem, you must prove that the hypotenuse is congruent to another hypotenuse, and the leg is congruent to another leg, and you have to also prove that these two 90-degree angles are right and are congruent to each other. Not only that, they can be only used on right triangles, because 2 episodes ago, we said a right triangle has a right angle. Any right triangle has a right angle. If it doesn't have a right angle, then it cannot be a right triangle. That's why the Pythagorean theorem right here is reinforced, to make sure that a triangle is noticed to be a right triangle, rightly a right triangle. The reason why we wanted to explain these rules in the first place is many people in our geometry class last year has been using the hypotenuse leg theorem even if the triangles are not right triangles. They would go on proving that that triangle is congruent to this triangle without understanding that if they were right triangles. You have to prove that the triangles are rightly a right triangle to proceed.
Seems like the engine is ready sooner than we thought it'd be. Let's get out of here.
This doesn't seem right.
So now I think we're confident of doing this proof. So given segment BC is perpendicular to segment AC. So we're going to say segment BC is perpendicular to AC. We're going to make a 90-degree angle and talk about it later. BD is perpendicular to AD. So here's BD and AD. Another right angle, but we're going to talk about that later. Again, segment AC is congruent to segment AD. So right here are going to be congruent. We have to prove that segment AB is an angle bisector. So we have to prove that this line, horizontal line right here, is an angle bisector. So here's our givens in a two-solution format. We have a statement and a reason. These three statements were all given to us. Literally given to us. So what can we say first about this proof? Well, the first thing that you might want to catch with your eye is the perpendiculars and how we drew the right angles. We are not sure that they are right angles unless we prove it and show it. Here's an example. We can say angle C is right. We could also say angle D is also right. And we could say for both of them, perpendicular lines can bring you right angles. We could also say that for the other one as well. If we're trying to use the hypotenuse length theorem, this is going to be unessential because we're trying to prove the main ingredient to this problem, right 90-degree angles. Are these triangles rightly right angles? Let's continue. We also have to find out if we want to find the two right congruent triangles congruent, we have to find and understand that angle D has to be congruent with angle C. Because since they're both right angles, we could say that all right angles are going to be congruent. And yeah, no matter how big they are, if they match with a big triangle or a small triangle, all 90-degree angles and all right angles are going to be congruent with each other. So we're going to say this is 90 right and congruent along with that one. Okay, so now we've proven that those two are right angles. The next thing we can talk about is, if we're trying to use the HL postulate, there's one thing that we're missing, another leg. And we can say that AB can become a leg. So AB is going to be reflexive with AB. And we're going to say that is reflexive. They're basically congruent to each other because it's literally the same thing. So right here, I'm going to change it to a different color. Yep, here we go. And I'm going to say red because that's reflexive. Now, what we have is a reflexive, two congruent angles, two congruent segments, and two congruent angles. So you know what the next step might be? Yes! We can finally prove our next step. We can now say, finally, we can use the HL theorem. So hypotenuse leg. So triangle ACB has to be congruent with triangle ADB. The reason why we do that is we have two right triangles. Now we have the permission with the rules to use the HL theorem. But we're not done yet. There are still triangles on the field we have to talk about. And we still have to figure out that AB is going to be an angle bisector for somehow. Or if you want to find that AB is an angle bisector, we need two congruent angles. But where? If we prove that these two triangles are congruent, then it also means that this angle and that angle has to be congruent. So we can say angle CAB, is going to be congruent with angle BAD. So angle CAB is going to be congruent with angle BAD. We're going to say corresponding parts that are congruent of triangles are congruent. So now we've proven that those two angles are going to be congruent to each other. And now we use our final answer. We have now proven it. So we can say segment AB is going to be a angle bisector. The reason why we can say that is two congruent angles is going to bring you an angle bisector. So there we have it. We have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 rows and 10 different steps to prove that segment AB is an angle bisector. So now AB is an angle bisector. Not only that, we've also learned how to use the HL theorem in a proof. And that concludes the video. I hope this video has helped you understand the HL theorem. Thank you for watching Top Fingerlines Math Industry. Like and subscribe!